And with that, please help me welcome our speaker for the morning, astrophysicist Dr. Nour Raouafi is a principal professional staff at Johns Hopkins University Applied Physics Laboratory, and he is the project scientist for NASA's Parker Solar Probe. Dr. Raouafi obtained his PhD in December 2000 from the University of Paris at Orsay, France, before joining the Johns Hopkins Applied Physics Laboratory in 2008. He worked at the Max Planck Institute for Solar System Research and at the National Solar Observatory in Tucson, Arizona. On the Johns Hopkins website, sir, you are quoted as saying that the data from Parker shows us how the solar wind gets going at its source. People have been wondering what causes solar wind for some time, and I hope you will tell us about this as the morning progresses. With that, Dr. Raouafi, welcome to the Greenway Talks online at Palomar Observatory. Thank you for taking the time to speak with us today. We'll take questions at the end of the presentation. You can type questions into the chat and we'll pick them up at the end. But for now, I'll ask everyone to turn off their microphones. And with that, Dr. Nour Raouafi, please, the floor is yours.
Thank you so much, Steve. It is a great pleasure to be speaking to you today, and to be also the first heliophysicist to address this great group, and it's an honor. And talking about Parker Solar Probe is always a fascinating thing for me, as I'm involved in the mission, trying to get it to work. Not sure why it's not getting into.
We can.
Okay.
Got it.
Excellent. It's a great pleasure to be with you today, and I'm going to I'll be covering a little bit of ground because Parker Solar Probe is not only about the sun, the corona, and the solar wind. We are also looking at other synergistic science that is fascinating, and we never ever thought that we would be doing that science, but here we are doing it. But let me start from the wide universe, and this is one of the deep field views by Hubble, and what we are seeing here are galaxies, stars, and you name it. And I like this type of scenes because it reminds me of my childhood. I was born in the countryside. We didn't really have too much light pollution, and in the summertime, when you look at the sky, it looks pretty much like this one, and it's just fascinating. And as a small kid, and I'm pretty sure everybody asked themselves, what are these bright dots we are seeing there, and what is going on there? And yeah, we grow up and we are still asking ourselves what is going on out there. And we are so lucky and fortunate to be living in the neighborhood of a medium-sized star, and that is active but is still gentle, that we can live in its neighborhood. And basically we are continuously immersed into its wind that we call the solar wind. And by the way, whatever the sun is, in a way, because of its proximity to us, it's kind of a laboratory to us. Whatever we learn from the sun and how it shapes its heliosphere, we can project it into other stellar systems that are so far away from us that we cannot observe in much detail. But why do we care? Let me play the movie. why do we care? As I said before, we live in the extended atmosphere of the sun. And as you can see from this movie here, the sun is very active. It has a magnetic field, and the magnetic field is changing all the time. And it ejected every now and then these big CMEs that can impact the Earth environment and more generally the planetary environment, causing what we call space weather. And one of the manifestation of space weather, when it is really severe, it is the impact on infrastructure here on the ground, but also in space, like the telecommunication spacecrafts, like the GPS, and but also it can impact the power grid here on Earth, like you see on this example here, that is in March 13 in 1989, where the northeast of Canada in the US had a blackout because of a solar storm. Now imagine that event was big, but not big enough, I would say. If we had a bigger event than that one, it might actually cause a much wider blackout. And you can imagine on the impact on the society, on the economy, and all that. It's so space weather is out there, and we have really to care about it. So that's one aspect why we are interested in understanding the sun and how it works. But fundamentally, as humans, we are curious. We want to understand what we are surrounded by, and how it works. And obviously, space is one of them, and the sun in particular is one of those objects that we really want to understand how it works. So let me go a little bit more in history, and this is basically to build up why we are times we're living now are so special. So when you look back at history, particularly the history of sciences and specifically the history of heliophysics, there are specific times when certain discoveries were made, and they basically changed the course of all the research that was being done then. And as examples of this is the observations of discovery of sunspots by Galileo in the early 1600s. And from there, we went to discover the whole solar cycle, and the solar cycle was discovered probably 100 years later. But to this day, we do not really understand how the solar cycle works, how it comes about. And we know that there is dynamo in the sun and in the interior of the sun that produces the magnetic field on a cyclic fashion, but we don't really understand how that works exactly. And in the near future, hopefully we'll have mission that will help us to understand that. Move forward to 1859, when Richard Carrington observed for the first time white light flares. These are one of the most powerful flares that we can observe on the sun. And by the way, these are all these two graphics here are hand drawings, and these folks are scientists, but they are also artists. They really got every piece of all the details of this region on the sun. They got him pretty much as we observe them now. But the discovery of Richard Carrington led to what we call now the space weather. And I already talked a little bit about space weather, but this is really the birth of the space weather as we know it now. Move forward, and you mentioned the great George Hale in 1908, when he discovered the magnetic fields in sunspots, and it's then when we discovered that the sun is magnetized to start with, and all the activity that we know now is basically caused by the magnetic field, as is shown by this movie here from the Solar Dynamic Observatory, which is a NASA mission. Move again to the late 50s and early 60s, when we discovered that, yeah, the solar magnetic fields, yeah, they cause flares, they cause magnetic field, they cause sun, they are the source of sun, basically they are at the base of sunspots, but also they cause a highly dynamic phenomena that we call the solar wind. That was predicted by Jean Parker, after whom we named the mission, but was confirmed by Marcia Nigabour, who's still living. She works at the LPL in Tucson, Arizona. And from there, that was actually the dawn of the space age. And from there, you can count the number of discoveries we've made over the last 60 years or so, which is just impressive. Now, the times that we are living now probably fit with this golden era that I just mentioned, just 4 of them. And the reason for that is we are exploring the sun and its atmosphere in manners that we never have done before. The Parker Solar Probe is getting closest to the sun ever. And with it, we are flying through the atmosphere of a star for the first time and understanding what is going on there. There are another ESA-NASA space mission that is a solar orbiter that will go out of the ecliptic to give us the first view of the solar poles. And the poles of the sun are so important for the dynamo and how it works, and that probably will help us understand also the mystery of the solar dynamo. Coming back to the ground now, we have a 4-meter telescope in Maui, Hawaii, that is the deepest solar telescope. It will give us observation with a resolution that is about 10 to 20 kilometers in size. This, you go back just a few years back, we were seeing this type of resolution in numerical simulations. Now the data is available online and we can see it before our eyes. We can compare observation to numerical simulation really one-to-one, and that's really unprecedented. So, and there are other space missions, by the way, that are also contributing to this. But these 3 big missions they come together basically in the same time, and they form another golden age for heliophysics. And it's just fascinating what we are learning from them. So let me go now to Parker Solar Probe and what are the science questions that we want to address with this great mission. So the first question is, when you look at the solar atmosphere, the solar surface, the photosphere and the chromosphere, they are at a temperature between 6,000 to 10,000 degrees. But when you move just a short distance above, the corona starts shining in extreme ultraviolet and X-rays, meaning that it's extremely hot. It's millions of degrees hot. It's over 300 times hotter than the solar atmosphere. And in many ways, that is counterintuitive, because from everyday experience, when you have a heat source, the further you move away from it, the cooler it gets. And obviously, that does not work for the corona. Why the corona is much hotter than the solar surface? That mystery was discovered in the late 30s. And to this day, we are still trying to understand it, but we are so close to understand that mystery. The second problem that we want to address with Parker Solar Probe is what we call the acceleration of the solar wind. And by the way, these 2 phenomena are linked. In a way, it's a bigger phenomena, but it has 2 facets in a way. But you cannot explain one without the other. They go hand in hand. If we understand the coronal heating, we'll understand the solar wind and the vice versa. So what is a solar wind? The wind is a flow of charged particles that are electrons, protons, and heavy ions that are continuously flowing away from the sun to fill the whole heliosphere. And the problem that we are having with this phenomenon is that lower down at the base of the corona, the plasma has very low speed, which is about 5 to 10 kilometers per second. But over a very short distance, these particles start flowing at hundreds of kilometers per second, meaning they are accelerated very fast. And in the same way, they are getting heated as well. So where do they get the energy to be so fast and so hot? That's actually the problem we want to understand. And this problem, as I mentioned earlier, was discovered in the early 60s. So it's 6 decades old, and we are still working on it. I mentioned earlier solar magnetic activity. Whenever we have a big explosion in the form of a flare or a CME, they will actually relate a certain population of particles to a good fraction of the speed of light. This population of particles, we call them solar energetic particles, and they can impact satellites in space, but they can also impact the power grid, as I mentioned earlier. That's the big third phenomenon that Parker Solar Probe will address. And so with these three phenomena, these are the pillars for the primary science for Parker Solar Probe. But let me say this. Parker Solar Probe is an exploration mission. It is flying through a region of space that we never visited before. And like the visit of Darwin to the Galapagos, whatever he observed there was a discovery. It's the same thing for Parker Solar Probe. Whatever observation we are making there is a potential discovery. And we will see it on the data later, examples of the data that I will show later. So how we are going to get closer to the sun? Getting close to a star is extremely hard. It's not easy at all. And that's the reason for that. It's because of the orbital speed of Earth. You have to slow your spacecraft down to get it too deep toward the star. And the way we do it, historically, people thought that we have to go all the way out to Jupiter, fly above the solar poles, and get so close to the sun within probably 3 to 4 solar radii. That back in 2006, 7, and 8, that idea was abandoned to a novel one, which is basically using Venus multiple times to gradually get closer and closer to the sun, and that's what we are doing with Parker Solar Probe. The advantage of this new mission, as we are doing it using Venus, is that it gives you a long mission. Parker Solar Probe, the primary phase of Parker Solar Probe is 7 years. The mission that uses the Jupiter flyby, if we are lucky, we will do 1 full flyby, maybe 2 at maximum, and each of them will last less than a day when we are close to the sun. So comparing 7 years to, let's say, just a few days, to exaggerate a little bit, I think the advantage, I would choose any time 7 years over the short mission that will go very close to the sun. But by the way, that idea is not abandoned totally. We are still looking at it probably in the future to implement the mission and go so deep into the solar atmosphere within probably 2 solar radii to be below the sonic point. And obviously, the ultimate goal for Parker Solar Probe is to get within 10 solar radii from the sun center. That is 3.8 million miles from the surface, and we will achieve that on the eve of Christmas of 2024. That is about 1.5 years from now. But on late December of this year, we will be at 11.4 solar radii. We will be 1.4 solar radii away from the ultimate perihelion, which is we are almost there in some ways. So how did we do this? Obviously, when you get very close to a star, the radiation environment, but also the photonic environment is so severe. And if you don't protect your spacecraft, you will lose it anytime. And if you don't have a shield that will protect your spacecraft and the payload behind it, we cannot have a mission like this one. And what you are seeing here, this heat shield for Parker Solar Probe that has, it's probably an hexagon or an octagon. It depends who you talk to. Without this, we cannot have a mission. And just excuse me, I have a sample of it. Yeah. So I hope you see it in the camera here. This is a sample of the thermal shield, and as you can see it here, it's 4.5 inches thick. It is basically carbon foam that is sandwiched between carbon composites. But on top of it, the side that is facing the sun, it has also a white plasma spray that was created specifically for Parker Solar Probe. And the reason we wanted that is to reflect as much light as possible, the light that is coming from the sun. So when we are closest to the sun on the eve of Christmas 2024, this side here will be glowing at 2,500 degrees Fahrenheit. 4.5 inches back, which is the backside of the TPS, will be at about 700 to 800 degrees. So within 4.5 inches, we already lost something like 1,800 degrees. And one meter behind, we will be at room temperature. And that's where most of the instruments reside. There are exceptions to that, 2 exceptions to that, but most of the instruments reside in the shade of the TPS, the thermal protection system, and they operate at room temperature. These are some specs about the thermal shield that I've already talked about. So in terms of payload, as I mentioned earlier, most of the payload reside on the bus. That is this hexagonal structure here. Here you see the only imager we have in the spacecraft Whisper. It's a white light imager. Obviously, we cannot look directly at the sun because the instruments will not work. So we are looking at the side of the sun and basically imaging the solar wind as it's accelerated from very close to the sun in the solar corona and all the way past Earth. Other than this imager, all the other instruments are in situ instruments. We have fields. It has 4 antennas that are mounted just behind the TPS, and the antennas themselves are exposed to the full solar environment, and they are made of titanium, but they will be extremely hot. It has also a 5th antenna, which is on the boom here, that is in the shade of the TPS, but that's the 5th antenna as well. And it has a set of magnetometers that are on the boom here as well. We have the solar energetic particle instrument, ESIS. It has this sensor here that cover the low energy part, but it also have other heads, this one and this 2 here, that covers the upper energy range. To measure the solar wind, we have the sweeps, the spans, which measure the protons, alphas, and electrons. But also we have a small instrument is on the other side of this graphic that is also exposed in the whole solar environment. And this is basically Faraday cap. That's the antennas and the Faraday cap are the only instruments that are exposed to the solar environment. We have Whisper, sweep, fields. Yeah, these are basically the 4 suites of instruments that do science for us. Let me now go to some science highlights, and I'm not going to start with the primary science of Parker Solar Probe. I'm going to start with synergistic science that we got from Parker Solar Probe. So every time we fly by Venus, we turn all our instruments on and try to gather as much data as we can around the Venus environment. And there are few flybys when the spacecraft flew behind the planet, and then we can deep really into the magnetosphere of Venus, which is an induced magnetosphere, by the way. But also Whisper can image the backside of the sun. And the initial program that we set for ourselves is trying to image the clouds in the atmosphere of the planet. And this is the first image we got from it. I think that was the 3rd Venus flyby. And when we saw this dark image here, and by the way, we are not really Venus specialists. So yeah, we were kind of excited. We thought this is the first image of clouds on the Venetian atmosphere. But we were kind of disappointed just a few days after, because the Akatsuki space mission, that is Japanese mission, imaged exactly the same region just a few years before Parker Solar Probe. And for us, it was basically, yeah, it was a nice image. I think we did a press release about it, and that basically was it. And by the way, this image is the image that is most shared on social media from Parker Solar Probe. I was giving a colloquium here at APL about Parker Solar Probe, and when I showed this image, and they basically said what I told you now, except that we have our colleagues here who work on Venus. They are Venus physicists. When they saw it, they were really excited about it. And immediately after the colloquium, they walked to me and asked, yeah, we need that data. We want to look at that data. There is way more science than you thought. And from there, what they discovered is the shortest wavelength thermal emission from the surface of Venus. But discovering this thermal emission at 7.5 micron is basically opening a new window into observing the surface of Venus. And by the way, there were several other missions that were dedicated to Venus. Some of them are they orbited Venus many times, and they did not really observe this emission. And by the way, this is the history of the discovery of thermal emission from the surface. And as you can see it from the 80s, that was the record was 1.7 micron. The 90s was 1.11 micron, and in the 2000s it's 0.85 micron. Parker Solar Probe now is at 0.78 micron. So this is the record now, and that's the new window that we are using. But this work from our colleagues here at EPL did not stop there. They did some modeling, and that involves transfer of radioactive transfer and all that. And when you compare this image here, which is the WSPR image, to the simulation with this, which is this one, they are very similar. And actually, what they are finding through their model is actually modeling the brightness of the surface is probably telling us many things about the composition of the rocks on the surface of Venus. And just to put it, as one of our colleagues here explained to me, is that we are probably scooping some of the future missions that are Venus missions that our NASA is building right now. They will look at the composition of the surface of Venus, and probably WSPR and Solar Probe is giving some hints toward that. Another aspect of Parker Solar Probe is dust. And we were concerned about dust since we started developing the mission, because dust is the only risk for the mission that we could not close. The reason for that is we know very little about the dust environment in the heliosphere, and I mentioned the risk because we have the solar panels are water cooled, and they have a network of tiny pipelines in the back of the solar panels, but also on the radiators. And if one of them is hit by dust particles, it might cause a hole there. All the liquid water will evaporate, basically, and that will put the mission in a really precarious situation. We don't want that to happen, obviously. But again, we don't have a dust instrument on Parker Solar Probe. So what we are doing is we use the whole spacecraft as a dust detector. Whenever a dust particle hits the spacecraft, it will evaporate, but in the process, it will also create a cloud of plasma, a small cloud of plasma, that will create a differential potential that will be detected by the electric antenna. And since we have 5 electric antennas, we can know at least the directionality of where the particle is coming from. We can also put constraints on the velocity and mass, although that's not really, because we only know the energy, the kinetic energy of the particle, and we cannot say exactly what is the mass, what is the velocity. We can just have constraints about that. So working on the directionality of the dust particles, for the first 3 orbits, we only saw one peak that is just before the perihelion. But for all the subsequent orbits, we saw 2 peaks. The one before the perihelion, that is a secondary one after the perihelion. So the first perihelion, we already know how to explain it with the known population of dust particles in the heliosphere. There are 2 particles, the alpha meteorites. These are orbiting the sun in near circular orbits, but there are the beta meteorites. These are particles that are ejected from the inner heliosphere to the outer heliosphere, and they are caused basically by collisions between the alpha meteorites. But this secondary peak here is kind of mysterious. and we could only understand it through modeling. And what the way we understand it now is you have the heliospheric zodiacal cloud. It is interacting with another stream of dust particles, and when the two meet, they through collisions they will create another population that is a beta stream of dust particles, and this is an animation of it. So you see the zodiacal cloud here. These are the what you are seeing orbiting the sun. That's the alpha meteorite. The blue here, the cyan, is the beta meteorites. But when we include the Geminids, and when they intercept the zodiacal cloud near the ecliptic plane, and through the collision, they will create the new population. This is the Geminid trail, and this is the new population. So we are, for the first time, we're observing the degradation of a stream of dust particles through the interaction with the zodiacal cloud. And by the way, there is another study that was published recently. It says that this beta stream of dust particles must actually impact the surface of the moon. What would be the impact of space equipment on the moon and maybe humans on the moon? We don't know yet, but at least we know it can weather the surface of the moon. Another one, and then after that, I'm going to the solar wind. But this is a fascinating observation, and in a way, we discovered it by chance. What we do to passively manage the momentum of the spacecraft, sometimes we flip it back and forth. So when you flip it, you reduce the momentum in a way. And using Venus through these periods, we can image both sides of the sun, the forward, but also the backward. And analyzing this set of images, what we did notice is this bright trail here. There is excess brightness there. Initially, when we looked at the inner part of the field of view, we thought, yeah, these are coronal streamers, like this one or this one. But when we looked at the outer telescope, yeah, we saw that the brightness continues all the way out. And we know that streamers do not make it all the way here. So this must be something different. And when we look at the orbit of Venus, which is marked by the red dots here, that trail coincides exactly with the orbit of Venus, which, by the way, Venus is this one here. So the interpretation of this is that we are observing a dust ring along the orbit of Venus. And this is the first time we've seen this. It's this dust ring here. We know that the Earth has a dust ring, but we never knew that Venus has one. And by the way, a subsequent study showed also that Mercury also has a dust ring as well. So the two innermost planets have dust rings, Earth has dust ring, and the outer planets has more prominent rings as well. But the mystery here is how these rings form. There are basically two theories. One of them says that these dust rings are primordial since the planet formed. Another dust ring is another theory is based on the gravitational trapping of dust particles by the planet. And these particles would remain for a long time orbiting the sun along the orbit of Venus. But after that, through collisions, they will be ejected out of the ring. And so there is basically an equilibrium between trapping and collisions to maintain the ring. But we cannot really tell which theory is the right one. Now I'm going to the solar wind, and this is, I think it will be one of the biggest achievements of Parker Solar Probe. As I mentioned earlier at the beginning of the presentation, one of the goals is to explain how the solar wind form at the source, what is its nature. And its nature, it means whether it is a continuous flow like the wind we detect at 1 AU, or it is intermittent in the sense that it is caused by individual events. But when the wind moves away from the sun, really at long distances, it gets homogenized through processes like turbulence and instabilities and all that. And the third example is how the solar wind is accelerated to escape the gravity of the sun, because we know lower down the particles do not have enough speed to escape the gravity of the sun. The escape speed is about 600 kilometers per second, but all the velocities we measure are below that. So the wind must be accelerated along the way to escape the gravity. Going back to the very early observations of Parker Solar Probe, and this is one of the very first data sets we got from Parker Solar Probe. This is magnetic field data from the magnetometers. From previous observations in the heliosphere, we, in the solar wind in particular, we are used to fluctuations like these ones. They are low amplitude fluctuations in the magnetic field, but also in the other plasma parameters. But when we got closer to the sun, what we are seeing here are humongous fluctuations in the magnetic field. And by the way, we got this data set 2 days before the AGU in 2018, and we were supposed to present them on, it was a Tuesday, and the Thursday we were supposed to present them to the public. And for about 10 to 15 minutes, we thought there is something wrong with the instrument, because we never seen such high amplitude fluctuations. But as I said, it took us about 15 minutes to realize, actually, no, what we are observing is physics. It's real. It's a real phenomenon. And there are two ways to explain it. Whether there are different polarities on the field, one of them is positive and the other one is negative, or you have really folds on the magnetic field, that the magnetic field rotates on itself all the way back to the sun and out. And the answer to this is actually the current sheets is wrong interpretation. What we are observing here are folds in the magnetic field. And these folds are everywhere closer to the sun. We see them all the time closer to the sun. They are also extremely energetic. And the reason we know they are folds in the magnetic fields and not current sheets separating different polarities of the field, there are two ways to do it. One of them, we look at the magnitude of the field. If it was a current sheet, we should see deep in the magnitude of the field, which is represented by red here, but we don't see that. On the other hand, we see the inversion of the radial component. By the way, most of the field close to the sun is along the radial direction. So that's why here I'm showing the radial component of the field. The other evidence to show that these are folds, there is a stream of electrons, we call it the strahl, that is always flowing along the magnetic field. And what we see is that the strahl follow exactly the field. The pitch angle, in other words, does not change, meaning that it's the same field line and the strahl is following it. So as you can see it here, this is basically the perfect definition of a switchback. You have the magnetic field at the beginning, it's at about 100 nanotesla. When we enter the switchback, we move to almost the minus 100 nanotesla. And after that, we come back to the ordinary state, which is the normal one. This is what it does to the plasma. Here we have a slow solar wind. Within the switchback, we go to a fast solar wind. So from about 300 kilometers per second to 700 kilometers per second. And after that, obviously, we come back to the slow solar wind, meaning that these switchbacks are highly energetic. They carry a lot of energy for them. And remember, to explain the solar wind, we are looking at a source of energy to heat and accelerate the plasma. So the switchbacks might be the smoking gun we are looking for, but there is more to that. And actually, they are going to lead us probably to the biggest discovery we are making with Parker Solar Probe. So the switchbacks. Let me go back to the previous plot. So the switchbacks, when you have a zoom on this zoom in on this region here, the switchbacks come in groups. Like this one, and this one. We call them patches. And the patchiness of the size scale of the patches correlates so nicely with the other structure on the surface of the sun that we call the supergranules. So that gave us a hint that probably the switchbacks are coming from the surface of the sun. So we started looking at the surface of the sun. What is going on there? Yeah, okay. Let me go out here. I'm going to share something else because the movie is not playing. I have to play it else. So let me see if I can play this. Let me share. Okay, do you see the movie now? I'm going to play it. So we started looking at the closer to the sun and what is going on. Let me make it in loop. That way, I don't have to loop it. And what we were looking exactly offline. What we discovered there are tiny explosions that are occurring all the time, and what they produce are tiny jets of plasma. So every one of these is an impulsive ejection of hot plasma into the corona and eventually into the solar wind. And by the way, when you look in particular at the poles, look at this patchiness also for coronal structures. You have a bright structure here, dark one here, bright one here, and there is the alternate dark and bright. And this probably hints to the patchiness of the switchbacks. So now what we think, when you look at movies like this one, that these small events on the sun, these are we call them jetlets. They are small jets of plasma. They are actually the birth of the solar wind at the source itself. The solar wind is created by tiny events. They are individual events, but there are so many of them that can power the whole solar wind. And by the way, we don't only see them at the poles, we see them elsewhere as well. So this can explain both the fast solar wind that is coming from the poles, but they can also explain the slow solar wind that is coming from the equatorial regions. Let me go back to the presentation now. Okay. I am not sure. You share. Okay. So I hope so. You saw what I wanted to describe in the movie, that these small jetlets are basically what we know they are giving the birth to the solar wind. But what is causing this jetting in the solar atmosphere? When you look at the magnetic field of the surface of the sun at coarse resolution, this is 1 arcsecond resolution from the HMI magnetograph on the Solar Dynamic Observatory. And all we can see is the strong field regions along the network, the magnetic field network. When you go to much higher resolution, this is 0.2 arcsecond resolution, which is 5 times higher than the HMI magnetograms, the scene changes dramatically. And we see opposite polarity magnetic fields everywhere. And that's exactly what we need, because to have reconnection, magnetic reconnection, you need the 2 polarities of the field. And this is what is happening. This is the movie of that that data from the Big Bear Solar Observatory. And we have a ton of small dipoles that are coming together to reconnect to produce the jetlets that I was talking about. So basically what is driving the solar wind is small scale magnetic field reconnection that is occurring all the time, all over the solar surface, both in the open field region to create the solar wind, but also in the closed field region to keep the plasma hot at coronal temperature. So this observation has a potential to explain both the heating and the acceleration of the wind, which is fascinating. Let me go back to Earth here and just give an analogy to this. When you go to vineyards, and in some places, when the wind is really harsh and it's so cold, what farmers do, they lit what they call candles all over the fields to protect their crops, basically to keep them warm and not freezing to death. And this has been done for millennia now. I believe I traced it back to the Phoenician, but it's being done to this day. In a way, the sun does the same thing, but in a more sophisticated way, using the magnetic field and all that. And it's really way more sophisticated physics to do it. That's how the sun keeps the corona hot and keeps also the solar wind flowing away from the sun. Let me now go back to the third objective of Parker Solar Probe, which is explaining energetic particles. We always hoped for a big event that erupts when Parker Solar Probe is very close to the sun. The reason for that is we want Parker Solar Probe to fly squarely through it, to sample the region where the energetic particles are accelerated. And we got that event on September 5th of last year, when an event erupted from this active region here. The CME from that event was, the speed of the CME was more than 2,500 kilometers per second. And guess what? Parker Solar Probe was at 14 solar radii. It was so close to the sun. This is the event as seen from by LASCO. As seen from Earth, it's a halo CME, but Parker Solar Probe was on the back of the side and was exactly in the right place to observe this. This is the movie from Parker Solar Probe from WSPR. And what you are seeing here, things are going well. We see the usual structure in the solar wind. By the way, we saw the Milky Way passing by. And all of a sudden, there you have it. You have this huge CME. This is the Milky Way, by the way. You see it passing by. So you have this huge CME hitting Parker Solar Probe with a humongous shock wave. And they can tell you, literally, it shook the spacecraft. The spacecraft was shaking, but it's really within the noise of what Parker Solar Probe can tolerate. So the spacecraft really managed that situation so well, because it was low. But the importance of it is that we never thought that events like this one will have an impact on a massive spacecraft like Parker Solar Probe, but still we saw it in the data. So what is really interesting about this event? It is, first of all, we are learning so much about the internal structure of CMEs. As you can see it here, it's extremely, extremely complex. The degree of complexity we are seeing from Parker Solar Probe, we never seen from one AU. The other thing is, I can tell you that we flew actually through the site where the particles are accelerated. The data we got from this one was early this year, but we are still working through the data, and the papers will be, we are coordinating some papers that will be published by summertime, but expect some big results from this one. It's fascinating. This is exactly the type of events we are looking for. There is just one thing I want to stop at it when it comes. Yeah. Yeah, let me, oh my goodness, go back, please. Yeah, do you see this trail here? I hope you see it. That's actually the Gemini trail. That's the trail of the asteroid Phaethon, which leaves a debris of dust along its orbit. And that is exactly the trail I was talking about earlier when I talked about dust. We also image it with Parker Solar Probe, with WSPR. We see it almost every orbit now, that every time we orbit the sun, we see this trail there. I'm at the end of my presentation. The last thing I want to say, if you want to learn more about Parker Solar Probe, there is an article, Physics Today, that was published last November. It's a journey to the sun. It's all about the history of Parker Solar Probe and what is the science we want to achieve with Parker Solar Probe, but also what are the highlights of the discoveries of Parker Solar Probe. You can have it there. I have the link here If you don't have access to it, please email me, and I'll be happy to send you the PDF of this article. With this, I'm happy to take any question, and I'll be happy to answer them. Steve, I think Steve, you are muted, I believe.
Well, yes, Dr. Raouafi, thank you very much. It's an amazing journey. And let me open the floor for questions. Turn on your microphones. Anybody? Okay, we had a couple of questions in the chat. Tom, you had one about the Carrington event, how Carrington event works. Would you like to come in and ask that question?
Yes, can you hear me now?
Yes, can hear you.
First of all, it was a wonderful presentation, Nour.
Thank you.
I've been involved in astronomy for 30 years, and the sun is just something that's not in the night. So you really opened up whole new vistas for me. The specific question I had was the Carrington event where the sun was blocking out the northeast. Can you describe that more and what actually was happening there, and what's the physics, and what do we do to protect against it?
Okay, excellent. Really an excellent question, and it goes back all to the magnetic field. So when the magnetic field emerges from the sun, it builds up complexity in the solar corona. And when you twist basically magnetic fields, you store energy in it. And the magnetic field can tolerate that up to a certain point, beyond which it has to come back to a lower energy state. And the way it does it, it reconnects. And when it reconnects, it releases energy to the plasma in the form of speed and heat as well. But again, when we have these big CME events or flares, they, as I mentioned earlier, they accelerate a certain population of particles to a good fraction of the speed of light. These are the energetic particles. Some of the outage that we see on the ground and the power grid in extreme events is caused by the energetic particles. That's one, but also by the CME itself. When we have the shock hitting the magnetosphere, they cause storms within the magnetosphere itself. They induced currents in the magnetosphere. And those currents will have an impact on the power grid. And that's sometimes we had example when you have electric transformers, they were completely burned because of this. That's what the Carrington event, the Carrington line event in 1989 was. But the original Carrington event caused the strongest geomagnetic storm ever recorded in history. There was no storm bigger than it. Basically, the wires of radiograph were basically burning. They caught fire. Let me mention another aspect of space weather that people don't. At least there is another event that is so severe as well, and that is, I believe it was in 71 or 72. That was during the Vietnam War. There was a strong solar storm. Geomagnetic storm caused by an event on the sun, and what it caused the mines in the bottom of the sea to explode, and the Marines didn't really understand what was it. They thought, yeah, the Vietnamese was doing that, but obviously they don't have the technology to do it. But only to discover later that it was actually the sun. It's a massive event that caused a lot of induced currents in the magnetosphere, and that was causing these bombs, submarine bombs, to explode one after the other. So having space weather, it has a security side to it as well. Let me give another example, which is space weather does not have is not only limited to extreme events. It can be a modest event that will cause big losses, and the most recent one was the 40 satellites from SpaceX. the way we lost them, it was not really a massive event from the sun at all. It was very modest, except that these events will have an effect on the ionosphere. It can breathe in and out. And that will cause drag for spacecrafts and all that. And the drag caused for the SpaceX satellites, actually what caused them to be brought down and burn the Earth atmosphere.
Very interesting. So is this just an extension of Maxwell equations type of electromagnetic radiation to the, negative 10th hertz or something like that?
Yes, yes. It all drives from there.
It's just a continuum.
Yes.
So the next question is there any way to harvest that energy for power rather than photovoltaic or thermal solar energy or in the sun in general? Is there other ways to get energy from the sun feasibly?
That's really a question to the future. We don't know. There are certain things we discover in the universe and on the sun and elsewhere that it takes years and years and years to exploit them here on Earth. So we don't know. That could be something we can do in the future, absolutely. But so far we don't know how to do it.
Thank you very much. That's very good.
Thank you.
Okay, let me ask, does the sun have an overall magnetic field, kind of like the Earth with massive poles, and then this chaotic activity coming from small scale events like this, or is it only the small scale chaotic magnetic fields?
It's both. The activity occurs at small scale, like I showed in the movie earlier, that caused give birth to the solar wind. But the big CMEs and flares, they come from massive magnetic fields that are on solar sunspots and active regions. So the magnetic activity occurs on different scales. It's basically a spectrum. It goes from very large scales to very small scales. The very small scales is potentially the nanoflares predicted by Gene Parker. And I think the movie I showed earlier, it's probably very close to the nanoflares. So in terms of activity, the sun, the magnetic fields on the sun are always changing. The nice thing about the magnetosphere of Earth, it's kind of static. It doesn't really change much. And thank God for that, because that's what protects us from the sun. But on the sun, the magnetic field is cyclic. It goes through the whole solar cycle. At maximum, the sun is extremely active. It produces a lot of flares, a lot of CMEs, and there are a lot of sunspots on the solar surface. But when it goes to solar minimum, things go very quiet for a couple of years, 3 years, and after that, we start the solar cycle, the other solar cycle again. So it's highly dynamic. And that is actually one of the big problems that we are having, is we are trying to predict solar activity, because if we succeed to make predictions that, this active region is going to produce flare or CME, we can potentially mitigate its effects on the Earth environment. Like for example, turn off certain instruments on some spacecrafts or completely change the mode of operation of certain satellites. But so far we have limited success to it. We have to rely on future missions to tell us how to do that. But once we succeed, that's actually one of the big goals for NASA and NOAA, that we have to succeed in predicting space weather like we do it here on Earth.
Let me go back quickly to Tom's Maxwell equation question. If we have moving magnetic fields, we're going to be generating electrical fields also.
Exactly. Yes.
Do those fields combine to account for the acceleration of the particles?
That's actually, yes, that's actually part of it. Let me go back to the solar wind because it's easier to explain than flares, and other ones are extremely complex. So, but for the solar wind, when I talked earlier about the low speed of particles, I was mainly talking about protons and heavy ions. They have lower speed, but the protons are so hot, they will be flying at maybe thousands or more than 1,000 kilometers per second. So the electrons will escape the sun much more easier than the ions. And once you separate these two charges, you will create an electric field between them. And that's actually one of the theories that it tells, yeah, that's how the solar wind is accelerated. But I think with the new observations we have, that's probably a small component of it, of the acceleration of the wind. It doesn't account for the whole acceleration of the wind, but definitely we have electric fields in the plasma of the solar wind, definitely.
Mhm. Thank you.
You're welcome.
Other questions? Anybody? Please jump in. I think we had a couple of other questions in the chat. Let's see. Mark Shed, you had a question about the magnetic switchbacks. Would you like to turn on your microphone and jump in?
Yeah, hi. I'm a little bit down with the flu right now, but so I'll keep my. I won't give you all my my flu face. But I had a question because one of the charts showed that with those switchbacks that you get a velocity increase up to about 700 kilometers per second or something. And I was just curious if because that is above the escape velocity needed of the gravity, is that part of the acceleration process for those flarelets or those small activities?
Yeah. So that go ahead, please. Okay. So this is what is fascinating about the switchbacks. Switchbacks are galvanic waves. These are basically waves in the magnetic field. And whenever we have reconnection lower down in the solar atmosphere in the form of jetlets, reconnection naturally will create alpha waves. But lower down in the solar atmosphere, the background magnetic field is so strong that the amplitude of the waves is small. So the switchback does not really form in the corona itself. But once that wave propagates outward, the magnitude of the background magnetic field will drop so fast, and all of a sudden the amplitude of the wave grows with respect to the background magnetic field. And that's how the way the switchback is formed. The switchback is formed by steepening of the wave. And the phenomena that I showed earlier of the differential speed, that occurs further away from the sun when the switchback is fully formed. Closer to the sun, I mentioned that the jetlets are impulsive by nature. They have high speeds like 300 kilometers per second to 400 kilometers per second. So we need a little bit of additional energy to escape the gravity of the sun. But again, the reconnection that is ubiquitous will create a spectrum of alpha waves. And these alpha waves will help accelerate the wind to escape of the speed of the sun. So basically, the reconnection will give you all the ingredients for the wind to escape the sun. First of all, it gives you the impulsive jetlets, but on top of that, it will give you waves that will push that wind, give it a kick to escape the gravity of the sun. And further out, the waves will keep heating and accelerating the wind.
Got it. So it's basically it's a synergistic system
Exactly.
of acceleration.
Exactly. Yes. Exactly. Yes. Yeah.
Thank you. Fantastic presentation.
Thank you. Thank you.
Other questions? Anybody else? Kathy, you had a question having to do with the switchbacks. Would you turn on your microphone and jump in on that?
Hi, thank you very much. That was amazing. I
Thank
was
you.
riveted through the whole thing, took pages of notes, by the way.
Thank you.
So thank you very much. And I believe you've already answered my question. So, are there repeated switchbacks, or is it just the one that's near the surface? And I think you've just answered the question in answering Mark Shed's.
Yeah, and let me just make a precision. Thank you, Kathy, for the question. The switchbacks, they were actually observed in the solar wind before Parker Solar Probe. I dated back them to the Mariner missions, and that was the very first report about them. But this is the the difference between why they are so important now. They were not, probably people didn't look at them same way before. The discoveries of the switchbacks before, we saw them every now and then in the solar wind. But when we got closer to the sun, they were everywhere. And that's actually what made them so important. With Ulysses, with Helios, with the Mariners, far away from the sun, every now and then you will see a fold in the magnetic field. But when we got closer to the sun, they were everywhere. And that's what Parker Solar Probe, in a way, it put them at the center of the stage. That's what Parker Solar Probe did. And that actually what led us to probably the discovery of how the solar wind is born.
Kathy, does that answer your question? I hope. I guess.
Yes, it did.
Thank you.
Absolutely. Thank you very much.
Kathy, you have another question about what was Parker Solar Probe a few days ago with the energetic CME. That's, I think, the CME that occurred. When was it? I think it's
About the 13th, 12th,
13th, yeah,
13th, yes.
Yeah, 12, 13. So Parker Solar Probe was just starting what we call the encounter. The encounter is when the spacecraft is below a quarter of an AU from the sun's surface. So Parker Solar Probe was at about 60 solar radii. And guess what? That event was also very fast. It was over 2,000 kilometers per second. And we were so lucky that it hit Parker Solar Probe head on. But except that we don't have the data yet. We have to wait for Parker Solar Probe to emerge from the encounter and start radiating data back to the ground. And we'll see what we got. But it's we cannot wait for that data to come down.
Yes, you had mentioned that it was going to be maybe this summer, and I had just pushed send, and then you answered that question during your presentation. But thank you. That was very exciting.
Thank you. Thank you.
And Tom, you had a question here. Maybe since we're running down on time, maybe a good question to end on.
Thank you.
What
I'm a student of philosophy of science, and Einstein imagined himself riding a beam of light and what the world would look like. And Jonas Salk imagined himself a polio virus and how he would behave. So I like to use this inverted perspective and ask, what would the world look like according to the sun looking back at the earth? And if we were the sun looking at various frequencies we're dealing at, and we used solar scale rather than human scale, and if this Maxwell's equation, if we went to the 1/1,000,000th of a hertz of frequencies and analyzing the energies that way. But I guess the question is there stuff happening at this incredibly low frequency that are just outside of our instruments that we're measuring? We're not used to measuring microhertz or whatever. And is there another way of looking at this energy transfer and correspondingly information transfer that at very low frequencies has incredible energy and information content?
Yes, I mean, your question is basically, that's the question for the future. And let me just give an example. Going back to that movie where I showed the jetlets.
Yeah.
When you go to lower resolution, by the way, also low cadence data that we got from Soho and like Stereo and others, these jetlets are there, except that the quality of the data doesn't give you access to it. With SDO, we have them there too, except that our minds didn't go to think about them. We have this data for over a decade now. It's only now when Parker Solar Probe gave us the hint, we went and looked for them. So yes, to your question, there is so much we are missing because simply we either don't have the right data or we don't have the knowledge to exploit the data we have. It's actually a combination of both. And just to tackle your question in a different way, there are different aspects of the sun as a star that we cannot really address through the ways we have been observing the sun for decades now. We are used to observe the sun from one point, one viewpoint. But the sun is a sphere. and it's changing all the time. And the fascinating thing about magnetic fields, they can connect regions that are so far apart, and they can transfer energy between them. And if you don't observe the thing as a whole, you are missing a lot. So we have now a mission concept that we submitted to the decadal, that basically it's constellation of spacecrafts that will observe the sun as a whole, gives you basically 4 pi steradian coverage of the whole sun. But not only that, we want comprehensive observation of the sun from the interior of the sun all the way to the solar wind, all at the same time. There is a problem that we have been facing for decades. We have pieces of data that can answer certain questions, but to answer another question, you have the data simultaneously. And if you don't have that, there is always a gap that we are suffering from. So the way to do it now is not only have the coverage in terms of space, but also the simultaneity of the data. And that's hopefully, I hope the decadal will recommend that mission, and because we need to observe the sun as a whole and as a system, coupled system, because the phenomena I talked about, you take, for example, the solar cycle, dynamo, solar activity, space weather, they are all interconnected. The physics of them is interconnected. And if you don't have all the data set that you need to explain all of them more or less at the same time, we will be always having knowledge gaps. But coming back to your question, absolutely, there are certain frequencies that we are not observing, and they probably contribute the most to the background phenomena. And the prime examples of those are the coronal heating and the acceleration of the solar wind. And my argument is for them is very simple. When you take solar minimum, you don't have active regions on the sun. You don't have these big sunspots that are causing these very complex magnetic fields in the corona that cause CMEs and flares and all that. But what you have is only small scale magnetic fields. So the heat, and by the way, the wind does not really care about the solar cycle, and the heating the same way. And when we are at solar minimum, the corona is still hot and the wind is still blowing, meaning that the primary driver of the wind and the heating is not the big active regions, it's actually the small scale. And when you go to higher and higher resolution, you see more and more higher scale magnetic fields and the structures that are coming out of them. So yes, to your point, we need much higher resolution, both in space, in time, but also in frequencies as well.
I guess one question to look at would be, what is the energy power distribution across the spectrum that we're observing? So yes. How much are we giving out in infrared, how much in photons and lights, whatever, and compared to the theoretical energy being generated by the sun. Yes. So how much energy is the sun, producing, and how much are we actually measuring through our instruments? And if we're not measuring that, where is it going? And is this actually a link into dark matter? But that's a whole nother discussion. But are we observing all the energy that we think the sun is presenting?
The term, I think the secret is in the term energy. If you are referring to the photonic energy, I think we know what is the spectrum of the sun. We know what it is, from all the way from X-rays to the far infrared. I think that one is, we know what it is. But the issue that we are missing is you have waves, all sorts of waves. And some of them are, we don't know much about them. That's also energy we have to cover. It's coming from the sun, but also we have the particles. And these are the two big things that we need more measurements to characterize the energy budget that is coming from the sun.
It just seems to me that's a good place to look for dark matter. And we have a pretty nice laboratory here instead of distant galaxies.
Absolutely, and I can tell you that. Well, by the way, the movie I showed earlier about the jetlets, I'm the one who led the paper, and it's published now in AppJ, just last month. If we explain the heating and the solar wind. By nature, when you solve a problem, you create a bigger problem. And I believe there are a couple of ideas out there. I don't think they are firm yet, but if they materialize, this will dwarf the coronal heating and the acceleration of the wind and all that. They are way, way more complex phenomena that we will be probably facing for decades to come. So, but we are still working on that. Yeah.
Thank you. Wonderful stuff.
Thank you.
If I can sneak in a question, I'm looking at the cover of the Physics Today and musing about the paths that these, let's call them jets. Some of these individual jets seem to follow a fairly straight trajectory. And I guess that means they're not interacting with whatever the interstellar medium is, and others have the twist and the switchbacks and so forth. And we know the switchbacks come from surface effects, these eruptive jetlets and so forth. Do the individual jets, if you will, are they fairly cohesive and maybe not rotating? And those are the straight ones, and the others have been disturbed by the surface phenomena?
Well, let me say first of all that the cover here is an artist's view.
Sure.
It's not realistic. What we are used to when we are measuring magnetic fields in space, there are always fluctuations. You cannot avoid, whenever we have plasmas, you will always have fluctuations. They are just natural. They occur naturally in a plasma. But sometimes you see the high amplitude, sometimes the low amplitude, but they are there. And by the way, if this is any close to reality, which is not, this is very close to the sun. Once you move way, way away from the sun, there are certain other phenomena that are born into the solar wind that basically will change the dynamics of the flow. And there are other things that are not operational close to the sun that becomes operational further out. Like, for example, shocks. Whenever you have streams of the solar wind slow and fast, when you move at 2 AU and beyond, you will create a shock there. And that will accelerate particles as well. That's what we call the co-rotating interaction region and those. So these shocks are not created very close to the sun. They're created further out because the conditions close to the sun are not ripe for them to be born there. And eventually, now talking about the limits of the heliosphere, eventually the solar wind has to leak into the interstellar medium. It cannot just be confined into the solar sphere, that is the heliosphere. How it does it? We have only measurements from 2 spacecraft so far. It's only Voyager, the 2 Voyager. That's all we have, and these are points measurements. So we eventually need way more than that. There is at APL here we have a mission concept that is also proposed to the decadal. We call it the interstellar probe. And unlike a Voyager that went to 100 something AU, the interstellar probe will go as far as 300 to 500 AU from the sun. That would really fly through the interstellar medium as the pristine interstellar medium. And one of the things also, it will give us a view of the solar system from the outside. And I hope again that the decadal will recommend that mission because it's just a fascinating mission. Yeah.
Thank you.
Okay.
Thank you very much. We are running almost an hour and a half. And Dr. Raouafi, you have been very gracious with your time. Really, we thank you very much. Great presentation. And with that, I think we need to wind the meeting down.
Thank you very much. It was really a pleasure talking to you and having this wonderful discussion with you. It's really an honor. Thank you.
Well, thank you. And with that, let me say something about our next meeting. The Greenway Talks Online will continue on Saturday, April 1st. Dr. Casey Law, research scientist with Caltech's Owens Valley Radio Observatory, is working on a new observing system that searches data obtained by the Very Large Array in real time and looks for millisecond timescale transient radio signals. This system represents one method among several that is being used to detect, localize, and characterize extragalactic radio bursts, fast radio bursts. Dr. Law will describe the technologies that have been developed and the discoveries that are being made in a presentation titled Fast Radio Bursts, Nature's Newest Cosmic Mystery. And let me add that because we are starting public tours here at the observatory, the Greenway talks will be suspended after Dr. Law's presentation. We'll start them back up again in November. Thank you again to Dr. Nour E. And thanks to everybody who showed up and participated in the discussion. Thank you very much, everybody.
Thank you.
Thank you.
And we'll
Have a
see
good
you on
day.
April 1st. Bye-bye.
Thank you. Bye.
Bye-bye.